Okay, thanks to the organizers for the invitation to speak here. So this is joint work with Havana Vinci. So I should say that the motivation of this is similar to the motivation that we saw in Raphael's talk, which is to construct 4 DT-QFTs. And so I'm going to outline some approach and give some examples towards the end of the talk. Okay, so in this first section, I'm going to motivate this topic of PDG algebras. And this was a program outlined by Havana over 10 years ago. And so the basic starting point is this Witten-Reshetikhin triav invariant for prime P. So it takes values, so Z of M3. It takes values in this ring of cyclotomic, in the cyclotomic ring, where OP is Z adjoint Q modulo the P cyclotomic polynomial and phi P of Q. So for prime P, this has a particularly easy form. This is Q to the P minus 1 plus Q to the P minus 2 all the way down to 1. So the starting point of Havana's paper was, well, if you want to categorify this three-manifold invariant, you first want to categorify the target of the invariant. So you would like to categorify this ring. And for no good reason, I just want to modify the goals just slightly. Instead of categorifying this cyclotomic ring on the nose, I'm going to talk about a slight modification, bold OP, which is Z adjoint Q mod the P cyclotomic polynomial, too hard, evaluated at Q squared. And the only reason for this small change is to match up with grading conventions in KLR algebras. But in principle, you could do everything just for this original ring OP. Okay, so what I'm about to describe is what Havana wrote in his paper. So the starting point is a field of characteristic P. And this kind of base algebra throughout the whole talk is this algebra, which I'll call HP, which is K adjoint D mod D to the P. So this truncated polynomial algebra, and we take the degree of D to be 2. And if we take the degree to be 1, then you would end up categorifying this original thing. Okay, and so this is a local algebra, and there's a unique simple module up to isomorphism. And I want to fix this simple module. So we let L equal simple one-dimensional module. Concentrated in degree 0. And since there's only one simple module, we very quickly conclude what the Grothendieck group of the category of finally generated projective, the category of finally generated modules over this algebra is. So the Grothendieck group of graded modules over this is just isomorphic to the ring of Laurent polynomials, where the class of a simple module shifted up by degree r just goes to the monomial Q to the r. And of course, this is not the goal. The goal is to categorify this more complicated ring. Categorifying Laurent polynomials is extremely easy. You could just do this with graded vector spaces. Oh, okay, forgot. Let's go here. And so, it's okay. Okay. So, in order to categorify this cyclotomic ring, the idea is to move to a different category than just this abelian category of graded modules. So we work in this stable category. So this is the stable category of HP modules. Thanks. And so this has the same objects as HP. but the morphism space is different. So hom in this category between two modules M and N. So it's the hom in the original category but then we factor out by some ideal, some subspace. And this subspace is, so IMN, these are all maps from M to N, which factor through some projective. So the hom spaces are different, smaller. Now, the reason why we want to consider this stable category in this context is this observation going back here is that, so now note that HP as a module over itself, projective module over itself, it has a filtration with subquotients L shifted by 2 all the way up to L shifted by 2 times P minus 1. So that means in the Grothendieck group, the class of HP is equal to 1 plus Q squared plus Q to the 2P minus 1, which by definition is our pth cyclotomic polynomial evaluated at Q squared. And well, if we look at the stable category, any projective module, the identity map of the projective module to itself factors through itself. So in this category, this projective module is actually isomorphic to 0. And so this relation that you want to kill is satisfied in the Grothendieck group. So I'll just write down one proposition. Is that the Grothendieck group of this stable category is isomorphic to this ring OP, which is a potential target for this homological three-manifold invariant. Okay. So that's the beginning of the story, and part of the Reshetikhin-Tarayev invariant is defined using representation theory of quantum groups at roots of unity, and we could think of these, and I'll talk about that in the next section, the decategorified story. But this representation theory you could think of as modules defined over OP. So want to categorify So this is just some general procedure, which we'll see later has some non-trivial examples. So this is the notion now of a PDG algebra. So let A be a Z-graded algebra over our field of characteristic P with a derivation of degree 2 such that d to the p is equal to 0. And so this is what's called a PDG algebra. And if p is equal to 2, this just recovers the normal notion of a DG algebra over field of characteristic 2. Okay, so it's a pretty natural algebraic object to study, and we're going to see that it's important if you want to categorify modules over OP. Okay, so let me take M a module over HP. This is just our truncated polynomial algebra, and N a PDG module over A. And all this means is that it's a module over A with a derivation of degree 2, which is compatible with the derivation on A. And so then M tensor N is a PDG module over A. So I need to describe the PDG structure and the A module structure. Well, the A module structure is easy. If I take an element A in the algebra and I act on this tensor, it just acts on the second tensor factor. And the D module structure is given by some sort of Leibniz rule. So it's dm tensor n plus m tensor dn. And there's some abusive notation going on here because this, well, in this first tensor factor, it's a module over this HP, which I say is generated by D. So we should think of this as the D in the algebra HP. And in the second tensor factor, this is the derivation on the module n, but I'm not going to bother making the distinction between the two. Okay, so this recipe describes a functor from modules over HP cross PDG modules over A into PDG modules over A. And so then taking the Grothendieck group, we get that so the Grothendieck group of this category of PDG modules is a module over this Grothendieck group, and this Grothendieck group is a module, so it's a module over this Grothendieck group, which is just the ring of Laurent polynomials, which is not quite what we want, because we want it to be a module over OP, but so we need to go a little further. Okay. And so I wanted to make a further categorical construction on this category APDG mod. So let's take two PDG modules over A. And if we have let's have a morphism between the two. So this morphism is said to be null homotopic if f is equal to sum, I goes from 0 to p minus 1, d to the I, h, d to the p minus 1 minus I, where h is some map from n1 to n2. And if p is equal to 2, then f is equal to dh plus hd, and so that just recovers the normal notion of a null homotopic map for DG algebras. And so now we let APDG mod underline be the homotopic category. So we quotient out by null homotopic maps. So this is APDG mod. Then we kill null homotopic maps. And so this is the homotopic category. And this is a good construction because this functor from over here now descends to a functor in the homotopic category. So there's a functor. So I'll rewrite what I had on the previous board, HPG mod cross APDG mod. To APDG mod, but now it descends to these kind of stable and homotopic categories. So now what happens is that the Grothendieck group of APDG mod underline, this homotopic category, is now a module over the Grothendieck group of this category, which we saw earlier was the cyclotomic ring. that's realizing our local goal of constructing constructing categorical modules over OP. And in practice, we have to make one further construction. So again, let's let F be a map from N1 to N2 between two PDG modules, APDG modules. F is said to be a quasi-isomorphism if, well, the fact that these are PDG modules over A means a couple of things. It means it's a module over A. It also has this, this structure, this D structure. And what you could do is you could forget about the A module structure and only think about the structure as an AP, as a HP module. Its D structure is the same thing as thinking of just its structure as an HP module. Okay, so if you throw away some information, you could say, so F is said to be a quasi-isomorphism if F is an isomorphism in this stable category. So you're losing a lot of information. You could ask, is it an isomorphism in the stable category? And if it is, you say it's a quasi-isomorphism. And then, okay, these quasi-isomorphisms form a localizing class. And so then we could let DAD be the derived category. So you invert all quasi-isomorphisms. And just as before, the growth in D group of this derived category is an OP module. Okay, so in practice, well, I mean, this is a pretty good achievement, but in practice, we have to go a little bit further and look in derived categories. Okay, so this is the basics of PDG theory outlined by Havan over 10 years ago. Any questions? Okay. So in this next section, I'm just going to review some things on the decategorified level, which we've seen in several talks already. So I'm just going to set up some notation for objects we're going to categorify for the rest of the talk. So this section is more classical. So this is just a review of quantum SL2. So I'm going to let U be the OP module, OP algebra, generated by, so this is the Bailenson-Lusztig-McPherson form of quantum SL2. So it's going to be generated by a bunch of idempotents, these divided difference elements, and the Fs. Subject to some standard relations. So first, as I said, these 1n's are orthogonal idempotents. The E's form a subalgebra. And we should be thinking of these things as evaluated in the ring OP. And then there's these mixed relations, similarly for the F's. Then we have this mixed relation, which basically says what this relation is on a weight space of a representation, 1n. So this is a sum over J. quantum A minus B plus n choose J, FB minus J, e to the A minus J. And there's a similar relation where F is in front. Okay. So this is our main object, which is U. And inside of U are some other important objects. So this is the small quantum group. So this is just the subalgebra generated by these divided powers where the exponents are just 1. And inside of here is the positive half of the small quantum group. And for SL2, this has a particularly easy description, and it's just a small generalization of the algebra we saw towards the end of Raphael's talk. This is just OP generated by E, but then we quotient by e to the p. This is a positive half of the small quantum group for SL2. Okay? And now for some of the representations we want to consider. Okay, so I'm going to let VL equal the Weil module for capital U. So this has a basis V0 through VL minus VL. It's L plus 1 dimensional. And with standard EF action. F is F raises a subscript. And E lowers. And we saw these objects also in Katerina's talk a couple of days ago. For L less than or equal to p minus 1, these Weil modules are irreducible. Otherwise, they're not. Okay, so this algebra U, it's a Hopf algebra, and so we could tensor these Weil modules together. And the two types of tensor products I'm going to consider later come of the form VR tensor VS, the tensor product of two Weil modules, and also the L tensor power of the two-dimensional Weil module. And I just want to say just one thing about this, in case we get to it later. Well, of course, both of these modules have a tensor product basis, inherited from the basis of VL. There's also canonical basis. And for VR tensor VS, the canonical basis is extremely explicit and very helpful for categorification. So this has canonical basis. VB diamond VD, where B is in between 0 and R minus 1, and D is in between 0 and S minus 1. And the definition of VB diamond VD in this case, so I could write it in terms of a single tensor product element along with the E's and F's. So this is equal to FD EA applied to VR tensor V0 if B is less than or equal to C. And the other way around, if B is greater than or equal to C, where, and I didn't tell you what, sorry? Right, yeah, where A plus B is equal to R, and C plus D is equal to S. Okay, yeah. Yeah, there was no A either. Okay, so, and of course there's a canonical basis here and on more general tensor products, and you could define it inductively, but this is kind of the base step. And so it has a pretty easy description here. Okay, so that is it for this section of quantum SL2. And so now I'll start describing how to categorify the things that we see here. Any questions? Okay, so in this next section, we'll see the first successful implementation of this PDG program, which is a good sign that it's possibly the correct setting to work in. So I'm going to describe some work of Elias, Chi, and Havanov, ultimately categorifying this Beilinson-Lusztig McPherson form of SL2. Okay, so first, and I'm going to introduce this nil-Hecke algebra, which we saw in Raphael's talk. Let's use slightly different notation. So this is the nil-Hecke algebra over our field of characteristic P. And it's generated by, and I'll give a graphical description of this. So we have these polynomial generators, yi, and we can think of this as a string diagram on n strands, and we put a dot on the ith strand. And we also have these generators psi I, where we have a crossing of the I and I plus first strands. And this is a Z-graded algebra where this has degree 2, and this has degree -2. And there are relations that we saw in the talk earlier, and subject to relations. So I'll just give a graphical description of maybe one of the relations that we saw earlier today. Bunch of relations, and then we put a dot up here. I'm describing the relations locally. So a dot up here minus a dot here is equal to 1, which is the same thing as a dot here minus a dot here. So that's it's the mixing relation between the yi's and the psi i's. There was another relation that we saw, psi I squared is equal to 0. So something like this. And these are these are homogeneous relations, which is why this algebra is Z-graded. Okay, and so now the next observation is that NHN is a PDG algebra. So I have to define what the differential is. So I'm going to define it locally on these generators. So D of a strand containing a dot, it just produces another dot. And then D of a crossing, it produces a crossing, a dot up there minus a dot down there. So this is how the derivation is defined locally, and then you extend to the whole thing by the Leibniz rule. Okay, so this is a PDG structure on the nil-Hecke algebra, so which leads to the first kind of big theorem in this area. So I should say that nil-Hecke algebra is the most basic example of a KLR algebra. nil Hakka algebra is the SL2 version of the KLR algebra, or the Quiver-Hakka algebra. In general, Quiver-Hakka algebras also have a PDG structure, but there are less theorems known about it right now. So this nil Hakka algebra, taking the direct sum of its module categories over all n, without considering the derivation, is known to categorify the upper half of quantum SL2. But now we have this theorem of Havanov-Vinci from a few years ago. So we look at the sum over all n of these derived, well, we look at the derived category of these nil Hakka algebras, and we consider the growth in D groups. And this is isomorphic to this algebra we saw in the previous section, the upper half of quantum SL2 at a root of unity. And a priori, this isomorphism could seem a little strange because this is a finite dimensional algebra, and this looks like it could be infinite dimensional. And so part of proving this theorem is showing that these derived categories collapse if n is big enough. And the other part, the main technical part of proving this is that when n is in the range where it doesn't collapse, that it actually has rank 1 over OP, the growth in D group. So these are two somewhat difficult results. And then in a follow-up paper by Elias and Chi, we could consider the KLR2 category. U for SL2. So I'm not going to really describe this. It's basically a doubling of the nil Hakka algebra. Has a derivation D such that the growth in D group of this derived category is isomorphic to this small quantum group. So this doubling of the category gives us the full small quantum group. And the derivation on this category comes from the derivation on the nil Hakka algebras plus derivations on these so-called cups and caps, if you know this KLR category. And then one final theorem in this section. This is in a follow-up paper by Elias and Chi. The KLMS 2 category. So this stands for Havanov, Lauda, Mackay, and Stosich. U dot. So what this category is, it's a graphical description of the Karoubi envelope of U. Has a derivation. Coming from the derivation on this category, along with derivation on so-called splitters and merges, such that the growth in D group of this derived category is isomorphic to this Beilinson-Luschig-McPherson form of SL2. So all the algebras we saw in the previous section have some sort of categorical analog now, which is a good sign of this PDG theory. Okay. Questions? Okay, so now I'll write down an approximate formula, which is probably wrong, but D of something like this. It's a sum where you put a dot. The sum is over the strands, and you put one dot on the strand with some coefficients. Yeah, okay. Yeah, I think so, but I can't remember. I can't remember if there are coefficients here. Or, yeah. to see if I missed anything. Okay. Okay, so in this last long section, I'll talk about categorification of representations. So first, we want to introduce this so-called cyclotomic nil-Hakka algebra. So this is a quotient, it's a finite dimensional quotient of the nil-Hakka algebra, where we quotient out by this ideal generated by y1 to the L. So in this diagrammatic language, if you have L dots on the farmost left strand, it's equal to 0. And this is a PDG ideal, so this is a PDG algebra. Okay, so forgetting about the PDG structure for a second, there are induction and restriction functors. So I'm going to call induction functors F, which go from the cyclotomic nil-Hakka algebra of rank n. And again, I'm going to forget about the PDG structure for a second, to the cyclotomic nil-Hakka algebra of rank n plus 1. And then there's E, which goes in the other way. Okay. And it's a fact that these satisfy categorical SL2 relations. And just as a small example, you have something like the functor EF is isomorphic to FE plus a bunch of copies of the identity functor, maybe with some grading shifts. And I should just write down some names. This construction works in greater generality for cyclotomic nil-Hakka algebra, cyclotomic KLR algebras. So just some people are responsible for this. So there's a construction. There's a proof by Kan Kashiwara. There's a proof by Webster. As we saw earlier today, the first kind of, well, the model example was in work of Schwang-Ruquier. And in a kind of Morita equivalent setting, this also goes back to, in a weak categorification sense, to Bernstein, Frankel, Havanov, and Straupel. And also in Aaron and Lauda's paper. So this fact is proved in various degrees of generality in these various works. Okay. And so there's a PDG analog of this theorem, of this fact. So these induction and restriction functors could actually be upgraded to PDG functors. And so I should say this is due to Elias and Chi. So there's an action of this PDG2 category on these PDG module categories. So everything which exists in the sort of classical world could be upgraded to a PDG statement. And then we could ask what's going on in the growth entity group. And for L less than or equal to P minus 1, this growth entity group of derived categories is isomorphic to this irreducible module VL, which is also the vial module. Okay, so we have a categorification of some vial modules and some irreducible modules by looking at the natural PDG analogs of these cyclotomic nil-Hakka algebras. Okay, so now for the rest of the talk, I'm going to talk about a way to construct categorification of tensor products. So, I should say, as we saw earlier today, there's this big machine of Raphael to construct tensor product categorification. There's also these graphical algebras of Webster. And so what I'm about to describe now is Morita equivalent to a construction of Webster. And the way I'm going to do this is by describing some work of Hu and Mathis. So Hu and Mathis construct certain modules over the cyclotomic nil-Hakka algebra. So first I'm going to introduce some combinatorial input into this. So I'm going to let P and L equal the set of L tuples with entries either 0 or 1. And in a more combinatorial language, you can think of zeros as empty slots and ones as boxes. And this is a more natural language because, well, what I'm describing is the SL2 version of what Hu and Mathis do. There's a SLN version which really uses tableau combinatorics in a more serious way. Okay. And so if lambda with n boxes. So there are L choose n elements in this set, which is going to mimic the dimension of a weight space of V1 tensor L. So if lambda is such a L tuple, we associate some monomial y lambda in this nil-Hakka algebra. Y lambda is y1 L minus a1, yn L minus an, where these AIs, well, they describe where the boxes in the partition occur, where the boxes occur in positions A1 through AN, read from left to right. So these exponents are strictly decreasing. And so now we form this cyclically generated module generated by this monomial y lambda. There's some grading shift, which I'm just going to ignore, which makes things nice. Okay, so there are L choose n such cyclically generated modules. And so now, right. And so now what I'm going to do is I'm going to take the endomorphism algebra of these cyclically generated modules. who in math is called the Quiversure algebra. So S and L is defined to be the endomorphism algebra over all these lambdas of these G lambdas. So this is what they call a Quiversure algebra. And this has the structure of a PDG algebra in a very natural way, where D of F, so F is an endomorphism of these modules, D of F applied to an element X, it's D of F of X minus F D of X. So this is a PDG Quiversure algebra. And again, this is just for SL2. They prove various theorems for higher rank algebras. Okay, and so maybe it's good to give an example of one of these Quiversure algebras. So let's take n to be equal to 1, and L is general. Well, in this case, the cyclotomic nil-Hakka algebra it's just generated by a dot, which is just, so it's just a truncated polynomial algebra. Well, you would say y1, but I'll just call it y. Mod out by this cyclotomic condition. Okay, and I'm just, for convenience, I'll call this algebra C. Okay, so this is a very simple nil-Hakka algebra. And the corresponding Quiversure algebra, we'll see, is relatively simple, but it has some interesting properties, even in this small example. Okay, so first, let's let lambda I be the L tuple where the single box occurs in position I. And so then, if you follow this recipe, this cyclically generated module, it's just generated by this monomial y L minus I. Okay? And so I guess when this box is all the way to the right, it's just the algebra C, it's projective. And if the box is all the way to the left, then this monomial, this exponent is really high and it's just one-dimensional. Okay, and in between we have various things. Okay, and so there are various maps between these G lambda i's, which is what we need to define this Quiversure algebra. So I'll just discuss a couple of important maps. There's a map phi I plus 1, which goes from G lambda I plus 1 to G lambda I, where y to the L minus I minus 1, this generates this module, goes to y to the L minus I. And then we have a map in the other direction from G lambda I to G lambda I plus 1, where the generator y to the L minus I goes to y to the L minus I. And you could check that these generate the entire algebra. Okay. So this element is in this module. Yeah. You might be tempted to write y the L minus I minus 1, but that won't be a map. Okay. So now to relate this algebra to things we saw last week in Tony's talks. So we'll hold on to this board for a second. I just want to define, we'll see an isomorphic algebra. So AL shriek, this is a quotient of a path algebra of this linear quiver with L nodes. So we have edges back and forth. So this looks a lot like the setup of the zigzag algebra that we saw last week. By relations, and the relations aren't quite the relations we saw last week. So first, a loop at the first node is equal to 0. And elsewhere, a loop to the left is equal to a loop to the right. So in the zigzag algebra of last week, well, the big difference is that you would take 2 steps to the right is equal to 0 or 2 steps to the left is equal to 0. We don't impose that relation, so this is a larger algebra. And this is essentially causal dual to the zigzag algebra. It's not quite, but basically is. So causal dual to zigzag algebra. And this by itself also has a PDG structure. This is a PDG algebra where d of, well, the idempotent I, which is just the path of length 0 staying at node I, is equal to 0. D of this path, which I read from I plus 1 to I, it appends a loop, which is good because it's supposed to be degree 2. And by the way, it doesn't matter if you, by the relations, it doesn't matter if you append a loop at I plus 1 or I. And d of this path is equal to 0. Then you extend by Leibniz rule. Okay, so this is an algebra AL Schriek. And these algebras are PDG isomorphic. Where, again, the PDG structure on here is inherited from the PDG structure as an endomorphism algebra. Okay. So now a theorem with chi from a few years ago. Well, one kind of an easy part is that the Grothendieck group of the derived category of AL Schriek is isomorphic to V1 tensor L, but definitely not this entire tensor product, but just a certain weight space. And in the notation of the second section, I'm truncating by this idempotent Y1 L minus 2. So this is like the second highest or second lowest weight space of this tensor product. And 2, and this goes back to, well, work of Havanov and Seidel, as we saw last week. There's a Bragg group action on this derived category. So this is a Bragg group on L strands, which acts here. And so we saw last week in Tony's talks that the Bragg group action on the zigzag algebra is basically determined by projective modules for the zigzag algebra. We're working in a causal dual setting, so the Bragg group action is essentially determined by simple modules. So part of proving this theorem is, well, without the PDG structure, you need to find projective resolutions of simple modules. Here, you need to find so-called cofibrant replacements of simple modules. So this is some PDG extra structure which you have to worry about. Okay, so this is a good sign topologically that things are working out, and this is a good sign kind of from the perspective of two representation theory that we're along the way to categorifying representations. And so maybe I'll end with this theorem. So this is recent work with Chi. So one, there's an action of this PDG2 category on the derived categories of these PDG Quiversure algebras. Well, I'll say it like this. And then you could ask what's happening on the growth in the group of the derived categories. And this should not be much of a surprise in light of this kind of small theorem over here. The growth in the group of these derived categories. Well, now this is a module over U because of the first part of this theorem. And what module is it? It's this Lth tensor power of the standard two-dimensional representation. And so just a couple of remarks about this Quiversure algebra. In some sense, this is very closely related to singular category O. It's also Morita equivalent to these algebras of Ben-Webster. They're smaller versions of them, but Ben proved that they're Morita equivalent, and we proved they're PDG Morita equivalent. And then, of course, one could ask, what about categorifying arbitrary tensor products of file modules or even other modules? And in previous work with Havanov, so I'll just say this quickly, can categorify the tensor product of two arbitrary vial modules. And part of this, the proof here is using so-called PDG quasi-hereditary structure. The proof here is quite different. It's using the canonical basis description on the growth in D group from earlier and being able to really construct kind of indecomposable modules over a category of modules for this tensor product. Okay, so I think I'll stop here. Thanks.
So why is this construction better than Webster's for the PDG business?
Right. So one thing is that the way we describe the EF action is a bit different. So we show that induction restriction functors that they preserve these category of G lambda modules, and then that somehow induces an action on the endomorphism algebra. Ben's description is completely graphical with adding a black strand or removing a black strand. And I think they're the same, but I'm not completely positive. It was just more natural for me to stay in this language of induction restriction.
It's easier in this way.
I find it easier. And also Ben's algebra is larger. There's so many idempotents that are needless, so this seemed a more natural approach to me.
Can you see idempotent or quasi-idempotent in the C1 tensor L? You categorize this D1 tensor L. The question is, we think about graphical calculus, so can you see,
Right.
for example, the quasi-idempotent?
You mean things like for Jones-Wentzel projectors, or? Yeah. So well, not quite in this language, but in the language of category O, you have functors from singular category O to Harish-Chandra modules and back, which categorify some of these things. And temporally Lieb action is categorified by some functors there. And there should be some analogs here, but that's definitely the next question. A good question is how to start categorifying this graphical calculus. But I don't know. Certainly not. I don't know yet with the PDG structure.
You have a break group action here?
No, so I hope that there is, but we haven't thought about this yet. One advantage of Webster's approach is that there is naturally a break group action there. I don't know exactly how to phrase this in terms of these Quiversure algebras, so maybe it is better to go, well, maybe some mix of both is good, but yeah, that's a good question, yeah. I don't know, but it's the next thing to do.
Just a question. Do you think it's possible to find, or do you already know a presentation of this
Quiversure algebra, well, in this simple case for SL2, by generator simulations. This would be most helpful.
Well, let me think for a second. And we do have kind of like a cellular basis for this. And we do have a graphical description kind of coming from Webster's graphical description. So I don't know exactly how to answer your question precisely, but we kind of have a truncation of Webster's graphical calculus, which I think might give a generators and relations presentation of these Quiversure algebras.
I mean, is it isomorphic to this Quiversure algebra introduced by Schrödinger and Webster?
It's the same.
Yeah,
It's the same, right?
yeah, it's the same. Yeah.
I mean, so I know that there was a master thesis of one of Katarina's students where this like SL2 case is working out, I think. But I can maybe better to
Yeah, I mean, we use this, I should have mentioned that paper as well. We use their construction to kind of PDG enhance it and get a nice PDG basis. Thanks.